then tomorrow we will start crash course introduction into how to use OpenFOAM. So as it says, bring an old laptop, because the operating system is so old that he doesn't know what USB 3 is. So if you can find a laptop with a USB 2 port, then it should be okay. Also, you can check how you address your BIOS and change it so that the boot sequence will start with a USB first, and then your own hard drive further down in the list. So that shouldn't change anything, as long as then you later in life don't try to boot it with a USB stick in, then you will say no operating system found. But it's an easy way to play around with your own laptop without actually having to install software or install a new operating system.
If I install OpenFOAM myself, do I need an old version of OpenFOAM?
No.
Like your examples depend on some kind of...
Yeah, just be aware when you install OpenFOAM on Linux, the two systems have to talk together. So if you take the latest version of Linux, then you risk you don't find a suitable OpenFOAM, it doesn't work. So you have to enter the openfoam.com and see, okay, what's the latest version I can use.
Yeah.
So they have to talk together.
If you compile it,
Sorry?
If you compile it?
In theory, you should be able to compile it yourself, yes. But I would be careful. You risk wasting a lot of time.
I have done it before. It takes 6 hours to compile.
Thank you very much, yes. But I mean, the things I'm going to show you will be very basic, so you can be quite okay with an old version, okay, of course. Okay, turbulence. We have been through most of it. At least the first part, the important part for you guys, if you think about the exam. Turbulence number 1. So today I will address the second part, and also a little bit about DNS. Now, let me take the overview first. So the first part, that was the practice in detail a little bit, how we do the turbulence modeling, the different rounds families, and so here I would say I will find the questions for the exam. The next 3 articles will sort of be examples, cases where we know the classical 2 equation models like epsilon will have problems. Rotational effects on a sudden expansion flow, backward facing step, and then a small inlet wall jet into a domain, and finally Couette flow. The last one here is about DNS and how to obtain the results from DNS. So we start looking at the first one. Make it a little bit bigger. So here you have the Ran's equations for this problem. It is a 2-dimensional problem, and it's steady state, no time derivative. You have the Reynolds stresses here, and then you have a sort of a strange term in addition, that is the Coriolis force. So you are in a rotating system, you're sitting in a relative coordinate system, hence the Coriolis now appears as a force, not as an acceleration where it belongs, hence the minus. And for this problem here, running with ordinary, let's see, the geometry should be here. Running with K epsilon, you have problems. I mean, K epsilon will have problems just with the backward facing step. I'll see if I can give you that as a challenge tomorrow or next week with open fall. With the backward facing step, what's interesting is typically sort of the main result here. How big is this vortex going to be? So we are sort of seeking the reattachment point here, where you have one streamline separating this primary vortex here, and according to turbulence, well, it should be 6, 7 step heights downstream. Using K epsilon, you can get any number from 1 to 20 step length, depending on your choice of models, wall models, and here the choice of mesh. If you are changing the mesh a little bit, you get a totally different answer every time. So the standard K epsilon, not so funny always. According to theory, we should have received what we call a grid-independent solution. So you simulate with finer and finer mesh until you see the solution doesn't change anymore. Then you are very happy. Then you sort of have a grid-independent solution. That's not possible with turbulent flow, K epsilon model. Every time you change the mesh, you get a totally different solution. So it's a real pain, to say the least. In this article, they then fight this problem with an ASM. If you can recall, a full Reynolds stress model, and RSM, that's where you have separate transport equations for all the different Reynolds stresses. And ASM, that was sort of a little extension of the standard K epsilon. So you solve K epsilon first, and then you just use algebraic expressions based on K and epsilon to evaluate the different Reynolds stress functions. So it's a very cheap extension of the K epsilon, but it involves a lot more physics. All of a sudden you have the possibility to simulate problems where the turbulence is not isotropic, which it must be if you are going to use K epsilon, or it should be. Of course, the danger here, you divide by epsilon, and if the flow becomes laminar, epsilon goes to 0 and everything explodes. But of course that will happen in the K epsilon model as well. So in this expression here, we have a production term, which you should recognize as a production term for a full Reynolds stress model. And this one is sort of exactly, I mean, the Reynolds stresses are unknown already, and just the gradient of the mean velocity profile, also unknown already, so no changes there. And also this gravity force, due to rotation, can also here be treated exactly. But of course, a lot of modeling has to be done here. Important, a wall function. It's sort of unavoidable with these turbulence models, ASM, RSM, to fight with a wall. So we have to treat the wall very carefully, very specially. So that also you will see in most turbulence models, what kind of wall model will you use. And normally you have a whole list to choose from. So there definitely you should play around with them, test them, validate them, verify them against any experimental data or some test cases before you make your final choice which one to use. It will depend on the Reynolds number and also of course of the geometry. So here the K epsilon equations. And as you see, it's mostly a model on the other side. The production term we can sort of work around. Dissipation has its own transport equation. And here, production term, diffusion term, and also the dissipation of the dissipation. Everything has to be modeled, so you can't use the exact equations, no way. So here they used a code called team, sort of the basis before Fluent was born. So it's a very old one. For the K epsilon model, you don't have many parameters to play around with, 1, 2 constants, and they will sort of be the same for most cases. You don't change them much. But the more advanced turbulence model you choose, ASM, RSM, you will have more and more constants to play around with. So here you see you have a good bunch of the constants, and then it is quite essential for your problem to find a suitable set of values, because these will change from one geometry to another, from one Reynolds number to another. So using these advanced models, ASM, full RSM, can be rather tricky, because starting here with a parameter study to find the optimum set, well, that's going to take years. So you are quite dependent on finding a suitable set from somebody, somewhere. For this case, they have given 3 different rotation numbers. A negative rotation, 0, and a positive rotation. So what will happen if you have a negative rotation, then it rotates like this. Okay, then this will be the pressure side, high pressure, increasing the turbulence. So then this wall will be unstable. The lower wall will then be a stable wall. You will damp the turbulence down. Rotating in a positive direction, the opposite will happen. Then you will increase the turbulence on the lower wall. Then it will be the unstable wall. And if you look into the streamlines, so the scale is not really correct here. This is a 0 rotation, primary vortex, and then the attachment length should be 6, 7 step heights. So here it appears to be 1.5 something. So it should be stretched much longer. When we have a negative rotation, the flow on the bottom wall becomes more laminar. So you enhance the length of this vortex. And positive rotation, increasing the turbulence, you have a shorter reattachment length. So the pressure, not that easy to see the physics there. One thing we can say already, if you use K epsilon only, you will get the center, the case B. He doesn't see the rotation at all, unless you can do something tricky with the K epsilon model, or else you can't really see the effect of the rotation whatsoever. Here, the different turbulent intensities, U flux square, V flux square, and clearly, yes, it's very inhomogeneous. So in the streamwise direction here, they're pretty strong. In the cross-stream direction, much weaker. So of course, it's a very inhomogeneous turbulent field. So, I mean, it's a very simple test case to set up, but not so easy to find. Yeah.
But you said that we can use the capital model if there is no rotation?
If it's no rotation, sure. Don't expect that good results though, because he has problems with his backward facing step. It's a classical test case for K epsilon, and normally he will fail very bad. You can get any reattachment length you like by changing the measure with it, so no, it's a very bad idea. K omega would be much better actually. He treats the walls better, and he's also better with recirculating flows. Adverse pressure gradients, he can handle that one better. The Reynolds shear stress, U-fluct, V-fluct. Clearly some differences here, yes. The negative rotation, soften it down, getting more and more laminar-like. Rotating in the positive direction, we increase the turbulent activity quite strongly. Some data has been given here by Walter and Johnston, finding the reattachment length as a function of the rotation number. So with zero rotation, you should be around 7. And negative rotation, more and more laminar, becomes longer and longer. With a positive rotation, increasing the turbulent activity, you will sort of mix it up faster, then you will have a shorter and shorter reattachment length. It doesn't exist that many experimental data with rotating channels. It's not that easy. You have to take the entire channel on a turntable, so it's a little bit messy. Yeah.
What happens to the ASM model for rotating flows, rotation numbers of 0.1, 0.2? Because it's quite okay on the left-hand side of it, and then it just flattens out.
Yeah, so you have a problem here. And I think if you had even increased, you will have more and more trouble. Why? Good question. Remember what happens. On the rotating side, you increase the turbulence. The turbulent activity gets stronger, meaning your smallest turbulent scale becomes smaller and smaller and smaller. You have to use more and more cells to resolve the flow.
Because they run the same grid for
Exactly. So they should have used finer and finer and finer mesh to really resolve it correctly. So here they are in trouble. Yeah, good observation.
Why is it then not on the negative side?
Because there the opposite happens. You sort of damp down the turbulence. Then it's easier to sort of have the spatial resolution okay. I mean, you have less and less activity. So
I thought
easier.
because you would increase it on the pressure side, but
Yeah.
there is just a flat wall.
Exactly,
Yeah.
and they are not interested in the upper wall here. They are focusing on the steps. So and here it's the reattachment length we are looking at. So, yeah. I won't go through any more of this. Skin friction coefficient. Change is quite dramatic when the flow becomes more laminar-like, negative rotation, and here you have this coefficient G that should sort of account for the rotational effect. And you see, if you switch it off, well then you hardly see the effect of rotation at all. If you switch it on, you get a totally different behavior for the skin friction. So capturing this rotational effect, oh yes, that's quite essential. Now you can find K-epsilon models with rotational terms included, so they try to capture this effect. How well they do it, I'm not sure. This is a rather old article, so I guess today's models may have this one more correct, but I would still be careful. Much better switch on a more advanced model like the ASM. Now let's look at the next one, if we can rotate it. Don't I have any option to rotate anything here? No? Yeah. Okay, let's try something else. Here it should be an option somewhere. Tools, maybe. That's great, thank you very much. There should be an option here to rotate it. I don't really see it.
In view, we can find
As in view, please.
view.
Where?
Move to venstre.
Get the top.
On the view.
Yeah, here we go. Rotate, which way was it?
Left.
To the left. Ah, wait, okay. So here is the problem. Again, very simple test case, easy geometry. Just make a small hole and send in a jet, and then resurface, and then a small opening here. So it's a steady state case. You will have one big primary vortex here, and then you should have some secondary vortices. Of course, the resolution here can be hard. You have a small jet entering here, and if this opening is quite narrow, then you need a lot of cells just over this very, very small area. It's quite essential that you resolve here the boundary layer correct. Well, that will depend, of course, which model you are using. And here they have done this with a full RSM model, if I recall correctly. So again, the Rahn's equation, Reynolds average Navier-Stokes, incompressible flow, and steady state, no time derivative, and we have the Reynolds stress here. And the transport equation then for the different Reynolds stresses looks like this one. The production term is exact, no model. But here, when we talk about diffusion terms has to be modeled, and then the pressure strain term, the redistribution term, the one that took energy from one component of the Reynolds stresses and gave it to one of the others. These has to be modeled. And finally, the dissipation, well, there we use a transport equation of its own, like in K epsilon. So it's a transport equation for epsilon. So here it's a two-dimensional case, so it's not that hard, but still you have a lot of unknown for different Reynolds stresses that has to be given their own transport equations. Diffusion terms must be modeled, and then the pressure strain redistribution is here split up into several parts, and again a wall model for it. Separate special wall function, because close to the wall, that's actually where the activity happens. That's where all the action takes place. So the growth, the sort of height of the jet entering in the lower left corner is here tested now with a full RSM. And Carlson did some experiments, and then you had the standard K epsilon models. So, yes, clearly some differences. And looking at the skin friction, I mean, now we are talking the frictional force on the lower wall. The changes become quite large. Now the RSM simulation here, absolutely, well, not perfect with the experiments, but at least much better than the K epsilon model. The experiments here, very close to the wall, must be taken with a grain of salt. It's very hard to measure them very close to a wall. So these points you should put a question mark on. But the overall behavior seems to be captured much better than with the RSM than with the K epsilon model. The average velocity, well, that's not so tricky to get. So even with a laminar flow, you will get a fairly decent velocity profile. So here the maximum velocity in the jet, how he decays from the max at the inlet, so 1. So smears it down a little bit. But you have to go pretty far downstream before the jet is totally killed. Yeah, some characteristics, some data compared. You know, you get this yourself if you like. So here the velocity profile again. The velocity itself, the mean velocity, is not that hard to get a decent value of. But it's a little dangerous because a small differences here from what it should be will have a very large effect on higher order quantities like turbulent intensity, turbulent kinetic energy. So you can hardly tell the difference here, but the effect is sort of hidden. Small differences may still be very important. So here an engineer would say, beautiful, all three works perfectly. No, that's not true. So the mean velocity profile is very important to get correct. And here plotted with the turbulent wall units, cross units, and the RSM. follows sort of the log law fairly okay in the beginning. So you see his closest position here, close to the wall, it's 25 or something in plus units. So he's fairly far away from the wall at the first grid point. This is something you have to be careful with depending on your wall models. Some models will require that you are in a Y plus of 1, 2, very close to the wall. You have to resolve the viscous sublayer, as we call it, very well. And that's impossible if you have a high Reynolds number. Just forget it. Then you have to use a more, say, high Reynolds number wall model, so that you can put your first grid point here in the log layer outside the boundary layer. Then the wall model has to sort of take the behavior into account with just models, or else you will get very, very strange results. So wall models, it's a fairly decent, important part of any turbulence model. Yeah, the different Reynolds stresses. So here you start to see some differences. Of course, the UV you can't find with K epsilon at all, so it's not in the graph at all. And here also the component in the streamwise direction. It's getting very tricky to get the experimental data to get this behavior correctly. Remember, he starts here with his simulation, the first grid point. So of course you can't mimic all this physical behavior very close to the wall. The wall model will sort of smear everything out. So what you then can hope for is to get a decent result in the outer region outside the inner layers. And also here the spanwise intensity, hard to get correct. It's a little low if you look at the differences here. But sort of an overall behavior, it's not that bad. The last example, that is a turbulent cuvette flow. So the geometry should then be something like this. Bottom wall stands still, top wall is moving with a constant velocity. For a laminar flow, you will have a straight line. A turbulent flow, you will produce this S-shaped velocity profile. It will still be symmetric around the center line. So here, before you start the simulation, you know what the average velocity is going to be. So this will now be 1/2 of the wall value as an average velocity. So you can calculate the Reynolds number before you start the simulation. What you don't know is what will this angle be close to the wall. There you find the wall shear stress. That one you don't know. Meaning you know the average velocity, you know the Reynolds number, but you don't know what force you need to achieve this flow? What force must you use on the top wall or the bottom wall as well to get the simulation running? As a contradiction to the Poiseuille flow. For the Poiseuille flow, you keep both walls fixed, and then you set up a pressure gradient or gravity as a driving force. What then? Well, there you will, before you begin, you can calculate the wall shear stress. Because if you look at a control volume inside your entire computational domain, then you can set up a control volume analysis, take a force balance. You know the pressure force, net pressure force acting on the entire fluid. That one has to balance the friction, the wall shear stress. So you can calculate the wall shear stress there before you begin. But then what you don't know is the velocity. What will the average velocity be? And what will the Reynolds number be? You don't know in a Poiseuille. So in a Toit, totally different. When you start looking into your Raun's equation for this very simple problem, very simple geometry, you can narrow it down to this. So here you will have sort of a total shear stress. Here you have the viscous shear stress, here you have the turbulent shear stress. And the sum of them has to be constant. There you have something you can test your simulation with. You know this one is going to be a constant, okay, then you just plot them together and see if you get a straight line. So that's sort of a test. How well have you solved the equation of motion overall? For this case, they did a full Reynolds stress model. So here the transport equations for the different Reynolds stresses. We have production, dissipation, redistribution, and then diffusion. So here some of them, it's a question if this term, shouldn't he belong together with epsilon? I mean, you have the viscosity and then the double derivative. Or you can even include him into the diffusion term, because you can always write this term as a dy of something. That's sort of a diffusion term, the space derivative in front. But that's just a definition here. So again, production term is exact, it's correct. No need to model that one. But for the rest, model. They have to be modeled. And then a long list of the chosen models here. And again, you see this redistribution term split up into several parts, and also here two different wall parts. And here, for this article, they played around with this wall proximity function, f, when you're getting close to the wall. So you sort of multiply the entire wall effect here with the function f. So then it's of course a question, what is the distance to the nearest wall? Well, you have two walls, so you have to take both into account, wherever you are. So they sort of played around with this wall distance d in this article. Not that many constants here, only 4. So, Bonder-Schema model. So, jump into the algebraic. Not going into that. So here the average velocity profile. And again, this one fairly easy to get correct, more or less. But even small differences here will be quite essential and will give rise to errors in other quantities. So here they compared it with the DNS that I did, if I recall correctly. Yeah. So the symbols here, they are from DNS that I did. So of course the DNS, that's the correct one. The straight line is in their simulation. Here you have sort of the control, the test. So you plot the total shear, both the viscous and the Reynolds shear stress, and because you know the sum of them is going to be constant. So this straight line here is just not a line drawn for in the figure. It's actually the sum of these terms, and then you check afterwards, is this one a straight line or not? If it is, okay, then at least you have got that part right. If it's a little change from one, okay, then you have to simulate further, getting the residual smaller, use more cells to resolve the flow correctly until this one is a straight line, because that's sort of unquestionable. It's a good test case. The different intensities. And here in the streamwise direction, oh yes, that's where most of the action takes place. And again, also here, very close to the walls. They peak very close to the wall. So here you have a lot of the turbulent activity. Here is where the production of the turbulent takes place. For the two other components, in the spanwise and the cross-stream direction, much lower. Also compared with some experiments. Also this cuvette flow, not easy to do in the lab, to create a moving wall. I've seen some setups using large cylinders with an elastic belt moving in both directions, but it will always waggle a little bit. They used a plate with a wheel on, and then rushed the plate across the floor, long corridor. But still, you have to run next to it and make the measurements, not so easy. So a moving wall, a little tricky to get correct in the lab. So here I don't think they compare with K epsilon at all. For this flow here, the K epsilon will have a lot of trouble getting this one correctly. Also, what you can see in the DNS simulation, that of course they didn't do in this two-dimensional simulation with the full Reynolds stress. So when you have this flow, you will, in this center region, and this is sort of what is interesting for a lot of turbulent modeler, if you increase the Reynolds number, these turbulent boundary layers is going to get sharper. This shoulder will become closer and closer to the walls. And also this one will be very, very steep. But then you will have a larger and larger center region where the velocity gradient is a constant. So having a constant du dy sort of simplifies your equations a lot, and then you can do a lot of investigation here in this center region. So that one is sort of interesting. But in the DNS, when I did this one, I had to do it in 3 dimensions. And then if you look in the streamwise direction, all of a sudden it started to occur these counter-rotating vortices. So in this region you will have this kind of behavior. Then that's a little bit tricky, because it's a question then, how wide is your domain? Is it wide enough so you have space enough for several of these vortices to coexist side by side? Because they have to be counter-rotating. You don't have a net spin in this direction in the cloud, so that one is something you really have to be careful with. So I can clearly see it in the DNS, but here it's not a part of the solution at all, since this one is only steady state and two-dimensional. So a little bit tricky. Of course, it's a question about these counter-rotating vortices in a quid flow, because people have having a hard time finding them in the lab. I can see them in the DNS simulation, so then it's a question, are they real? So there I have some argument with my colleagues in the lab, so I tell them I don't believe it until I see it numerically. Laboratory experiment, nothing to do with reality, of course. It's the numerics that counts. I don't know, they don't really agree with them. Strange. Anyway, if you want to buy a CFD software, you want to test it, at least here you have a very easy geometry, simple setup, where you have some results, and they may appear simple, these problems, but they can be a little bit tricky. So, it's a good set of test cases, I would say. Okay, any questions before we jump to DNS? Okay, let's take a break.